Everyone, welcome back. Let's try another simple example about our combustor. Okay, I know I have a stupid sense of humor. The example title still gets me. So, we have a gas turbine combustor. It's got inlet temperature of 800 Kelvin. Okay, that's kind of similar to what we had in our problem with the compressor. And a total pressure of 2 megapascals. Air mass flow rate 50 kilograms per second. We've been using that so far. And a ratio specific heat of 1.4 and 1004. 1.4, and a specific heat of 1004 on the entrance. As a note, because we're adding so much heat to our flow, we have to use a different ratio of specific heats and specific gas constant, or specific heat for the exit of my combustor, because the temperature is too different. I can't just assume it's 1.4 and 1004 anymore. So keep that in mind. The combustor is really one of the few places we have to do this. Okay, so what are we burning? Well, it's a hydrocarbon fuel, so my heating value is 42,000 kilojoules per kilogram, and it's going in there to kilogram per second. And my burner efficiency is pretty high, which is expected. Okay, so we have a whole lot of information here. Let's get to it. So first off, let's find out the air to fuel ratio, which is honestly really simple because it tells you what the fuel mass flow rate is and it tells you what the air mass flow rate is. And so it's just the ratio of those two. So mass flow rate of fuel over mass flow rate of air, so 1 over 50 is simply 0.02. You can expect this to be a fairly small number. Okay, so let's figure out the exit temperature now. How do we do that? Well, conservation of energy. So I have energy entering, some from the fuel, some from the air. This is coming from my compressor. This is coming from burning the fuel. And then that will give me fuel that's exiting. Now, if I can solve for this final enthalpy, I can then solve for my final temperature. As you know, I could do a whole bunch of algebra right here. I'm going to do it just in one step and then a second step. And a bunch of algebra. So, first off, we'll solve for that initial enthalpy. Okay, so I've rearranged this a bit. Now, remember that my enthalpy at the entrance is simply my specific heat at the entrance times its temperature. So that's this 1004 and 800. Then I have to add in how much fuel I'm putting in there. This is my fuel ratio right here. And I have my heating value of my fuel and then my overall efficiency, how much of that actually makes it to heat. And finally, in the bottom, I have simply how much is flowing out, more or less. How much is flowing out to figure out my enthalpy. So what I then get is my exit enthalpy is going to be 1,606.8 kilojoules per kilogram. And so if I don't want to, I can then solve for the temperature. So I divide my enthalpy by the specific heat, this time at the exit of the combustor, and I get a temperature of 1,390 Kelvin. Okay, the last thing is simply what is my total pressure at the exit. As a note, it kind of gives it to you in the problem statement. It says the total pressure at the combustor exit is 96% of the inlet total pressure, which tells me it's simply going to be 96% of whatever entered my combustor, which comes out to be 1.92 megapascals. So once again, this is not too terrible. This is what you can kind of expect for just a basic evaluation here. For any engine, you have so many parts. We're not going into super detailed examples for each individual part because you're going to be doing all of them. You're having to do an entire analysis of a full engine eventually. And so that's where it begins to get more complex as you connect all the parts together to make different engine types. So this seems too simple. There is a reason. It's because I'm more or less taking one big problem and breaking up into nice little cohesive chunks. So thanks for watching. I'll see you all next time. Have a good one. Bye-bye.